Imagine driving down the interstate. No stops, no plugs. Your car silently charging itself as you move. From city to highway, from dusk to dawn, the road beneath you becomes your power source. Welcome to wireless roads, charging while you drive. You're watching Drive Tomorrow, where the road ahead is always electric. This is the future of mobility. Charging an EV today means plugging in, waiting, and planning. It's the trade-off of electric freedom. But what if that trade-off disappears? What if we built roads that charge cars as they drive, at all speeds, over any distance? This is not science fiction. It's being tested now. Around the world, engineers, automakers, and governments are quietly laying the foundation for roads that transmit power invisibly through the ground. In the next few minutes, we'll explore how wireless roads work where they're being tested, what challenges stand in the way, and how they could transform every drive on Earth. Think of a world where range anxiety vanishes, where you don't need to stop to fill your battery. Wireless roads, also called electric roads or dynamic wireless charging systems, are embedded with coils or conductive strips beneath the asphalt. When your car, equipped with a receiver coil, drives over them, energy transfers across the air gap, no cables, no plugs. The road becomes your charger. Your car becomes a moving battery. If scaled, this could completely change how we build cities, plan transit, and even design the cars themselves. EVs would no longer need massive batteries. Instead, they could rely on continuous power from the road, making them lighter, cheaper, and more efficient. Transit systems could run indefinitely, fleets could stay in motion 24/7, and highways could become the backbone of national energy networks. At the heart of this technology is inductive power transfer, the same physics that lets you charge a smartphone wirelessly, but on a massive scale. The road has transmitter coils, and the vehicle has a receiver coil. When alternating current passes through the road coils, it generates a magnetic field. As the vehicle moves above, the receiver coil captures that energy, converts it to electrical current, and stores it in the car's battery. The trick lies in maintaining this transfer while the car is moving. For that, engineers use dynamic wireless power transfer, DWPT, or moving field inductive power transfer, MFIPT, systems that allow the magnetic field to follow the vehicle in real time. Dozens of coils are embedded in sequence under the road surface. As the car approaches, sensors activate only the coils beneath it, transferring energy seamlessly and turning off once it passes to save electricity. Challenges remain. Alignment is key. The car must stay centered above the coil path. Efficiency can drop sharply if the distance between the road and receiver coil increases. There's also the issue of seamless handover between coil segments, ensuring no power drop as the vehicle moves. And then there is infrastructure complexity and cost. Embedding thousands of coils beneath asphalt is no small feat. But advances are accelerating fast. Engineers are developing AI-based control algorithms, including LSTM-driven vehicle motion models that predict a car's speed and position, dynamically adjusting the power field for maximum efficiency. Standardization is also underway. The SAE J2954 standard now defines levels of wireless charging power from 3.7 kilowatts home systems to 500 kilowatts industrial and highway applications. That means compatibility between car brands and road networks could soon be possible globally. And this isn't confined to laboratories. Real roads are already coming to life. In Detroit, Michigan, a section of 14th Street near Michigan Central Station has inductive coils embedded under the asphalt, built in partnership with the startup Electrian. When equipped EVs drive over this lane, their batteries recharge in motion, demonstrating the first dynamic wireless charging system on a U.S. public road. In France, construction is underway on a section of the A10 motorway to test embedded inductive charging technology for trucks and passenger cars. Coventry, UK, hosts the Dynakov project, testing both stationary charging pads and dynamic lanes in mixed urban traffic. Sweden, a pioneer of electric roads, has tested multiple approaches, from overhead conductive rails for trucks to buried coils and conductive tracks for smaller vehicles. The E-Road Arlanda project near Stockholm was one of the first to charge vehicles while driving on an open public road. Even in the U.S. Midwest, Purdue University and the Indiana Department of Transportation are building an electrified highway segment designed to charge EVs at up to 65 miles per hour. The research focuses on concrete durability, electromagnetic safety, and cost optimization. These pilot projects show the dream is not only possible but within reach. The benefits could be enormous. If wireless road scale EVs could achieve effectively unlimited range without carrying huge batteries, charging downtime would shrink, and vehicle costs could drop as smaller batteries become viable. Over time, the cost per kilowatt-hour delivered through these systems could become cheaper than fast-charging stations, especially once infrastructure is widespread. Smaller, lighter EVs would use less material, lowering the environmental footprint of production. More importantly, wireless roads could integrate directly with the electrical grid. They could absorb surplus solar and wind energy during the day, channeling it into vehicles dynamically and shutting off during peak hours when grid demand rises. Roads would become active energy networks, intelligent surfaces balancing supply and demand in real time. Imagine highways that power semi-trucks in motion, or city streets that charge rideshares and delivery vans between stops, eliminating charging congestion. From a city planning perspective, this could revolutionize transportation. Charging infrastructure could be embedded into bus routes, logistics hubs, and urban corridors, creating continuous power loops across entire regions. In developing nations, electrified roads could bypass the need for thousands of standalone charging stations and help stabilize national grids by functioning as distributed energy storage. Of course, every technological leap comes with barriers. Building wireless roads at national scale is expensive. Installing coils beneath asphalt requires excavation, precision alignment, and ongoing maintenance. Each kilometer of dynamic road can cost hundreds of thousands of dollars, though prices are expected to fall as production scales and manufacturing improves. Efficiency remains another major hurdle. Inductive charging across air gaps loses more energy than wired connections. Current prototypes reach about 85 to 90% efficiency, but high-speed applications aim for 95% or more to compete with plug-in chargers. Alignment tolerance, the gap between vehicle coil and road coil, must stay within centimeters to maintain power flow. Any unevenness in the road or misaligned driving path can cause losses. Then there are standards and compatibility. For this technology to succeed, automakers must agree on uniform communication protocols and coil designs. Without global standards, a BMW might not charge on a Toyota-compatible road, or vice versa. The good news is that alliances are forming. The SAE, ISO, and IEC are collaborating to unify wireless charging interfaces so any EV can interact with any road segment worldwide. Safety is another concern. The idea of high-power electromagnetic fields under public roads raises valid questions about interference, object detection, and environmental impact. Engineers are developing shielding and smart sensors to prevent stray fields from affecting pedestrians, pacemakers, or metallic debris. Testing so far shows fields dissipate within a few centimeters, safe for people, animals, and nearby electronics. Still, strict regulations will be needed before mass deployment. Durability presents another frontier. Roads endure extreme temperature swings, heavy vehicles, and constant wear. Embedding fragile electronics into this harsh environment requires robust encapsulation, modular replacement design, and real-time monitoring. Many pilot programs now include IoT-based diagnostic systems that track coil health, magnetic strength, and energy throughput, alerting maintenance crews before failures occur. Governments also face a funding dilemma. Who pays for these roads? Taxpayers, automakers, or energy companies? Some nations envision public-private partnerships, where road operators install the infrastructure and charge vehicles automatically through digital billing systems. Your car could identify itself to the road network, pay wirelessly per kilometer, and even sell power back when not in use. Over the next decade, you might see hybrid roads, where only select lanes or sections are electrified, for example, truck corridors or urban bus lanes. As adoption grows, charging on-demand systems will activate coils only when a registered vehicle is above them, maximizing efficiency. Integration with renewable power sources will allow roads to draw electricity from solar farms, wind plants, or grid surpluses during off-peak hours. In the long term, autonomous vehicles may take full advantage of this ecosystem, coordinating speed and lane position with road sensors for optimal charge and alignment. The impact could extend far beyond convenience. Wireless roads could reshape the economics of electric mobility. If vehicles require only half-size batteries, automakers save billions in lithium, nickel, and cobalt procurement. That reduction in raw material demand could ease global supply strain and lower the environmental toll of mining. Smaller batteries mean lighter cars, improving efficiency and extending range even further. This ripple effect could reduce the total carbon footprint of transportation by double digits worldwide. In freight and logistics, electrified highways could eliminate the need for massive charging depots. Heavy trucks could run continuously across continents, powered in motion. For public transit, electric buses could charge along routes without ever stopping, improving schedules and reliability. Emergency and service vehicles could operate indefinitely during disasters, supplied by self-powered streets. But perhaps the greatest long-term potential lies in grid symbiosis. As millions of EVs connect wirelessly while driving, they form a vast, moving energy reservoir. In theory, each car could temporarily store power and return it to the grid when needed, a concept known as vehicle-to-grid (V2G) integration. Combine that with smart roads, and the result is a self-balancing, resilient global energy system. Cities could adjust traffic flow and charging schedules dynamically to match renewable output. Internationally, the race to develop these systems is intensifying. The European Union has committed funding through its Green Mobility Framework, while China has announced plans for its own electric highway corridor by 2030. The United States is exploring tax incentives and demonstration zones under the Department of Energy as Vehicle Technologies Office. Meanwhile, private companies such as Electrian, Qualcomm Halo, Momentum Dynamics, and Futuristic are driving R&D with field tests across multiple continents. Looking ahead, the first decade of wireless road expansion will likely focus on freight routes, bus corridors, and smart city zones. As costs fall, urban and suburban areas will follow. By the 2030s, entire expressways could serve as continuous power lanes, transmitting hundreds of kilowatts per vehicle. With economies of scale and renewable integration, operating costs could drop below those of gas or even hydrogen fueling. Imagine a morning commute where you never think about charging. You simply drive, and your car charges itself invisibly through the asphalt. The hum of tires becomes the sound of energy transfer. Every mile you drive contributes to a balanced, sustainable grid. Overhead wires and charging stations fade into history, replaced by a seamless energy web built into the roads we already use. The revolution isn't in the car, it's in the road. Our highways, once symbols of fuel consumption, could soon become engines of clean power. The hum of tires, the whisper of electrons, the pulse of the planet, all connected under one surface. Our world is shifting, roads fueling movement, energy flowing beneath asphalt. This isn't tomorrow, it's becoming today. If you enjoyed this exploration, hit like, subscribe, and stay ready, because on Drive Tomorrow, the road ahead is always electric.